Thank you, Kevin. I'm going to say a few things about the history of elliptic curves in cryptography, and then discuss elliptic curves, just what they are for those of you who might not recall that, and specifically elliptic curves over finite fields, and then introduce a simple crypto system based on elliptic curves. And then I'll start talking about various ways of choosing the elliptic curves and how the decision about how to do that relates to various unsolved problems, very difficult unsolved problems related to elliptic curves. Then there's a section about cultural background of elliptic curves that I'll probably skip for lack of time, but they are in my transparencies, and if anybody wants a copy of that. And here the idea had been to talk about things like the connection between elliptic curves and Fermat's last theorem, about the congruent number problem of ancient number theory and its connection with elliptic curves, the Birch-Swinnerton-Dyer conjecture, and the Sato-Tate distribution. These are all very interesting sort of down-to-earth questions related to the number theory of elliptic curves, but they don't, as far as I know, have any direct cryptographic application, so I'm going to skip those. And then I'm going to come to a brief discussion of why the discrete log problem on elliptic curve is thought to be difficult, or was thought to be difficult when we proposed using elliptic curves. And please interrupt with questions at any time. If I have time, I'll even explain this shirt to those of you who don't know the story. This shirt came about as a result of an activity here at MSRI for graduate students, a 2-week short course on cryptography that I gave last June along with Alfred Menezes and Simon Blake Wilson. And it's a tradition here at MSRI in these graduate programs that they have a T-shirt at the end. So this is the one we came up with. Okay, so it basically goes back to 1985 when Hendrik Lenstra developed this really intriguing and unexpected method of using elliptic curves for integer factorization. And at least in my case, I don't know if it was true of Vic Miller, but it was that the preliminary news about his factorization method that caused me to think about other uses of elliptic curves in cryptography. And it was within the same year that Victor Miller and I proposed using elliptic curve groups in cryptography. In a way, 85 is this sort of banner year for elliptic curves. Just by coincidence, that was also the year when Gerhard Frey proposed the connection between elliptic curves and Fermat's last theorem. So elliptic curves really saw all sorts of new applications in that year. I think the most important sort of basic new development related to elliptic curve cryptography that's happened since then was in about 1991 when an algorithm was proposed by Menezes, Okamoto, and Vanstone that gives sub-exponential time solution of discrete log problem for supersingular, for a very special class of elliptic curves. During the 1990s, elliptic curves have been worked on a lot in practice. There's been a tremendous amount of discussion and debate about elliptic curves in recent years and even recent months, as you're probably aware. Okay, but it's not that there's been any sort of striking new developments that I'm aware of in elliptic curves in the last 5 years or so. It's more on the practical side, there's been increased interest. Okay, so first of all, the general definition of an elliptic curve over a field F. So F for us will be a finite field, but the definition is for over an arbitrary field, for example, the real numbers or the complex numbers. It's an equation, you can think of it as the points that xy that solve an equation of this form where the a's are whatever your choice is of coefficients, some fixed coefficients. And there's a condition that it must be a smooth curve. And that makes sense over an arbitrary field. You simply specify there must be no point where all the partial derivatives vanish. This equation can be simplified a lot if f is not a field of characteristic 2. For example, you can make just y squared on the left-hand side, but the characteristic 2 case is a particularly important one in applications. And in that case, one distinguishes between the so-called supersingular case, where you don't have this term on the left, you can eliminate that term on the left, and the non-supersingular case, where you can eliminate this term. So when you have the xy term, that's non-supersingular. There are other much more natural characterizations of supersingular versus non-supersingular, but in the case of characteristic 2, you can distinguish between them by just looking at what's on the left of the equal sign, whether or not the xy term is there. And when the xy term is there, that's a non-supersingular. So one way to define an elliptic curve is a set of points that satisfy this equation together with a point called the point at infinity, which we denote O, which turns out to be the identity element. The point at infinity turns out to be the identity element of the group. So to illustrate how you get a group, let's look at the case of elliptic curve over the real numbers. Here's the elliptic curve y squared equals x cubed plus 8. This is slightly different. You're probably used to seeing, and whenever someone gives a talk on elliptic curves, they show the addition law by a diagram like this, except that it's much more common to have an elliptic curve that has 3 points of intersection with the x-axis. So just for variety, I'll show you an elliptic curve that doesn't have this little sort of circular-looking part. Yeah?
You started using the term non-singular, singular, and supersingular over here. Are you going to say more about what the origin of the terminology is?
I don't know what the order, why they. It's a misleading term because nothing to do with singular. That is, an elliptic curve is non-singular by definition. So, an elliptic curve, a supersingular elliptic curve is non-singular. So it's a sort of a bad choice of terminology, and I don't know why that terminology arose. But in any case, as I said, there's a much more sort of conceptual definition of what supersingular means, rather than just saying, well, it depends on what these coefficients are. Is that what you mean?
Yeah, well, I was going for a loop by your definition, your introduction to the terminology supersingular.
That's just in characteristic 2. It so happens that the supersingular condition is equivalent to this coefficient going out. But that can be calculated, but it's not the way one defines the terms. Okay. Yeah, I could say some more natural characterization of supersingular a little later. Just remind me if I don't. Okay. So the way you add points, if you have 2 points, you draw the line through them, and then there'll always be only one additional point where the line intersects the curve, and you take the symmetric point, and that is the sum. Well, here we're including multiplicity. It's conceivable that, for example, P1 could equal P2, in which case the line joining them we take to be the tangent line to the curve at P1. And then if you draw a line tangent to the curve at a point, there'd be one additional point where it hits the curve, and then you take the symmetrical point. That's, by definition, the sum. Now, it's not clear from this definition, something that has to be proved, that this way of adding points satisfies the usual properties of addition, the group law properties. Particularly, associativity is a little bit tricky to prove. That takes a little work to prove that. Now, another nice visualization of elliptic curves, if we take the field of complex numbers, then you can visualize it as a torus, that is the product of a circle with a circle. That is, the group of the elliptic curve, when an elliptic curve considered over the complex numbers, can be thought of as a product of two circle groups. That is, you can parameterize the points by two angles, one that goes around that way and one that goes around that way, and the addition law under this parameterization becomes equivalent to just the usual addition of angles around the circle. And this is a nice thing to keep in mind because it shows how elliptic curves are, in a sense, one notch more complicated than the most familiar group, which is the circle group. And this sort of rather simple observation, or rather basic observation, actually goes a lot deeper than one might think. For example, in the number theory of elliptic curves, a tremendous amount of work was done over the last 30 years or so on constructing analogs to the algebraic number theory of cyclotomic fields. Now, a cyclotomic field is an algebraic number field that you get by putting in roots of unity, by adjoining roots of unity to the rational numbers. And the roots of unity are the division points, the equally spaced points around the unit circle in the complex plane. Well, people got the idea of looking at equally spaced points around the elliptic curve, that is, division points on the elliptic curve, and developed a tremendous amount of algebraic number theory for the fields that you get by adjoining those points. And it was that type of direction that ultimately led to Andrew Wiles' proof of Fermat's last theorem. So this analogy between the cyclotomic algebraic number theory and the elliptic curve algebraic number theory is very deep and very important. Okay. Well, research on elliptic curves, or the equations of elliptic curves anyway, goes back very, very far. Gauss found formulas for, what amount to formulas for the number of points on the elliptic curve, of the form y squared equals x cubed plus a constant times x, where you think of this as a congruence modulo a prime p, that is, you work in the field of p elements. In the case in p, it's congruent to 1 modulo 4, and also a similar family of elliptic curves in the case in p is congruent to 1 modulo 3, and showed how that can that's equivalent to know the number of solutions of those congruences mod p is equivalent to expressing p as a sum of two squares in the first case, or in the form of a squared plus ab plus b squared in the second case. And this is actually, you can construct perfectly good elliptic curve cryptosystems using these elliptic curves. You'll get non-supersingular, nice elliptic curves, and you can use Gauss's method to count the number of points. And in fact, this is one of the easiest ways to count the number of points on an elliptic curve. Let me restate that. This is a family of elliptic curves for which it is particularly easy to count the number of points and know the number of points, and then you can test to see if the number of points has the right properties, and you can use such a curve. So that all goes back to Gauss. Okay, just one terminological thing, that elliptic curves, the term elliptic curves does not come from ellipse. That's what a lot of people think. That's why I don't like to use this example of the elliptic curve where you have this thing here that you've probably seen, because the first thing people think is that that's an ellipse, and you have elliptic curve and ellipse. It's completely wrong. Etymologically, the reason why they're called elliptic curves is because of elliptic integrals, and elliptic integrals arise when you try to find the arc length of an ellipse. So that's the connection with ellipse. It's not that they look anything like ellipses. Okay. Now, in cryptography, we work with elliptic curves over a finite field. Now, the rules for adding points, although the picture only makes sense over the real numbers, but that picture leads to algebraic formulas that express the coordinates of the third point, that is the sum of P1 and P2, as an algebraic function of the coordinates of P1, the coordinates of P2, and the coefficients of the defining equation. And those algebraic rules can be used over an arbitrary field to give, and they'll give an addition law. The same axioms will hold. The axioms only depend on the algebra, not on the geometrical picture. So everything carries over to a finite field. We have a group we have the elliptic curve group over a finite field in that case, and that will have a finite number of elements because clearly the coordinates of the point come from finite sets, so there are only finitely many possibilities. A basic theorem of Hasse says that the number, if you have an elliptic curve defined over the field of Q elements, the number of points on the field is not too far removed from the number of elements in the finite field itself, namely the number of points on the elliptic curve is within twice root Q of Q plus 1. So here's one possible characterization of supersingular is that if this term on the left, the thing that's in the absolute value sign, is divisible by P, the characteristic of the field, we say that it's supersingular. Otherwise, we say that it's non-supersingular. If you just pick an elliptic curve at random, it is almost certain to be non-supersingular. Okay, so that's one possible characterization of supersingular curves, are curves such that the number of points on the curve, not counting the point at infinity, is divisible by P, which is the characteristic of the field. Okay. Now, one useful fact about elliptic curves over a finite field is that, well, you can take your elliptic curve whose coefficient is defined over a pretty small finite field and then choose to work over a field extension, some finite extension of that field of definition. So let's suppose that we have our elliptic curve whose coefficients are in a field FQ, and we simply regard the same thing, since the field FQ is contained in this bigger field, FQ to the R power, we can regard the same elliptic curve as also defined over this larger field. In other words, we simply take x's and y's. Instead of taking them in our little field, we take them in this bigger extension with the same coefficients of the equation. And then we let n sub r denote the order of the elliptic curve considered over this bigger field. Now, a basic formula du Duvet it tells us how to find the rth n if we just know the first one. In other words, we have this elliptic curve defined over this very small field. It's quite easy just by any algorithm you want, just by some exhaustive method, to count the number of points, number of solutions of the equation over that small field. And what Vey allows you to do is immediately, very easily, compute the number of points over any extension that you're interested in. And here's the formula. What you do is you form a quadratic polynomial called the characteristic polynomial of the elliptic curve. You take this q plus 1 minus n1, which is the negative of what's in the absolute value sign. You make that the coefficient of p. And you look at the roots of this. An equivalent way of stating Hasse's theorem is to state that this particular quadratic polynomial has complex roots, does not have real roots. That is, the discriminant of this quadratic is negative. That's equivalent, or non-positive actually, and that's equivalent to this inequality. Anyway, you take those roots that are these complex conjugate roots, and you can express the rth n as the complex absolute value squared of alpha to the r minus 1. So for example, a very simple example occurs if we take those two examples that Gauss worked on, but if we take the case when Q is congruent to 3 mod 4, which is the opposite of of the more interesting one, which I had before. Or the second example, when q is congruent to 2 rather than 1 mod 3, then it turns out n1 is simply q plus 1. And from that, you get a very easy formula. That is, in that particular case, the coefficient of t is 0, and you get a very simple formula for n sub r. This case is not the most interesting for practical applications, because this case, when q is congruent to 3 mod 4, for the first example, when q is congruent to 2 mod 3 for the second example, turn out to be super singular. And so in cryptography, we probably aren't going to want to use those. But OK. So now, before going farther, I want to describe a simple crypto system and make some comments about what we look for with elliptic curves. And this is going to be the elliptic curve analog of the Diffie-Hellman key exchange that Kevin went through in the last hour. So here's the setup. So Bob and Alice want to agree on some common key that nobody else is going to be able to know. You have an agreed upon elliptic curve over an agreed upon field that you're not keeping secret. You exchange information on what that is over the open airwaves, and also a point, a sort of base point that you also don't care if everybody knows. Then Bob chooses a random integer k, which he keeps secret, and sends the point k times p. By k times p, you mean p added to itself k times. It's the elliptic curve analog of raising g to the kth power in Kevin's notation. And he sends k times p, that particular point, to Alice. Alice does likewise, choosing a random integer L, which he keeps secret, and sending the point L times p to Bob. The common key is k times L times p, which both can compute because Bob knows k and also LP, so he can use the middle expression, and Alice knows L and also KP, so she can use the expression on the right to compute it. Now, in order to think about the security of this, what does an eavesdropper have to do? An eavesdropper has to solve the elliptic curve analog of the Diffie-Hellman problem, that is, knowing k times p and L times p, she has to be able to figure out k times L times p. This can be done if she can solve the discrete log problem on the elliptic curve. And here's the discrete log problem. It's a very simple problem to state. You're just given 2 points on the curve. You want to find an integer such that the second point is equal to k times the first point. Now that's assuming that such an integer exists. In other words, assuming that q is in the cyclic group generated by p. Assuming that q is a multiple of p, find such a multiple. Find the multiple that it is. And in practical applications, q always will be a multiple of p. So we'll just state it this way. Given p and q, find the integer such that q is equal to k times p. So it's a very simple problem to state. Just have an elliptic curve. Somebody gives you 2 points on it, and they just want to know what integer you can multiply by the first point to get the second point. If you can solve this problem, then you can clearly solve the Diffie-Hellman problem. That is, the eavesdropper, knowing kp, because that's sent out over the airwaves, will be able to find out what k is, because p is also publicly known. And then, yeah. And not, because it comes from the finite field. It was first, the discrete log problem was first considered in the multiplicative group of the finite field, where the group law is written multiplicatively, so you're raising to powers. And that was the situation Kevin talked about. If you know g to the k and you want to find k, it's analogous to taking a logarithm in a discrete group. So historically, the terminology was just taken over from that group. And we just use the same term in order to emphasize the analogy. But you're right that since we're writing the group law additively, it might be more natural to say we're trying to divide by k. But by analogy, we call it the discrete log problem. Okay. So the discrete log problem on elliptic curve can be solved easily if the number of points, the order of the group, has no large prime factor. This is true of any group. You can state the discrete log problem on any group, and if the order of that group is smooth, that is the product of small prime factors, then it can easily be, the discrete logs can easily be found. And very easily, if it so happens that your elliptic curve is defined over a prime field and the number of points is exactly equal to the size of the prime field, which will almost never happen, but you can construct, it is possible to construct an elliptic curve over the field of p elements that has exactly p points, and the discrete log problem is very easy there, and that's worked by Nigel Smart and independently Sato and Araki, and probably Samayev was the first to do essentially that a few years before. In any case, that's been recently talked about, although it was probably done actually a few years ago for the first time. And if E is supersingular, then you have the Menezes-Okamoto-Vanstone algorithm that will solve the discrete log problem sub-exponentially, although not trivially, not extremely easily. What it does, it reduces the discrete log problem to discrete log problem in a suitable finite field, which can be solved sub-exponentially in that case, but it's not a trivial matter to do that. Otherwise, to the best of my knowledge, nobody knows any reasonable algorithm in any other case. Yeah, that's a good point. That the point P does not necessarily generate the entire group of the curve. In practice, since we're going to choose elliptic curves whose order of points is divisible by a large prime, all we really need is for the cyclic group generated by P, for its order, that is the order of the point P, to be divisible by a very large prime. It doesn't have to include the other factors. Typically, the order of the group E will equal a large prime times some small factors, and it doesn't make much difference whether the order of P is divisible by those small factors. All we care about is it's divisible by the large one. And from a sort of probabilistic standpoint, if you choose a random point, it's almost certain that its order will be. So in practice, it's not a major issue. Yeah. In fact, they're usually, well, cyclic or close to cyclic. They're usually cyclic or a product of a cyclic group times a very small factor. They'll be either cyclic or they'll have two cyclic components. Okay. So now how do we choose the curve? Well, we want to choose a curve such that the order of the group, we want to choose a field and then a curve, an elliptic curve over the field, so that the order of the group is divisible by a large prime factor. That's one of our basic objectives. There are three approaches to choosing a curve, and in each case, the basic question, I mean, there might be some other, well, there are a few things you might keep in mind when you choose the curve in addition to having a large prime factor. There's a test you should perform to be sure that the Menezes-Okamoto-Vanstone algorithm won't give you a sub-exponential time approach to the discrete log problem. You want to check that if you're over a prime field, the number of points is not equal to P. There are a couple things like that to check, but those are more or less, those are almost certain, those tests are almost certain to be met. and they're very easy to perform. The most interesting or the most sort of non-trivial test thing that you have to look for is for the order of the curve to be divisible by a large prime. That's the thing that is most likely to fail if you're not careful. Okay, so the first approach is to fix what's often called a global elliptic curve and vary the prime. So that, for example, define global means in characteristic 0. So that if you define y squared equals x cubed plus ax plus b, characteristic 0, any elliptic curve can be brought to this form, where a and b are ordinary rational numbers, then what you can do is choose an odd prime p and consider the mod p version of the exact same equation, which is what I had on the board on the screen in the particular case of example, the Gauss studied. We had an equation x, in that case, y squared equals x cubed plus ax, that we were looking at modulo p. So you can reduce this, you can consider it, instead of as an equation over the rational numbers, you can consider it as a congruence modulo p, where p is any prime that doesn't divide the denominators of the coefficients or the discriminant of the cubic on the right. That's because of the condition in the definition of elliptic curve that it's a non-singular curve. But there will only be finitely many p's that are bad, that we have to avoid. And then for any other p, for any rather large p, we can consider the elliptic curve obtained by reducing the coefficients modulo p, and let p vary until we get a p that we're happy with. So we choose p to be of a sufficiently large so that the number of points is large enough for our security needs, and we choose p such that the number of points modulo p is divisible by a very large prime. Okay. Now, the number of points on that elliptic curve will probably not itself be a prime number, because there's a sort of obstruction to primality of the number of points, which is that if our original elliptic curve over the rational number has non-trivial torsion, by which I mean a point of finite order. That is, if there's a finite subgroup in the group of rational points on the elliptic curve, as there often is, then that point of order 2 or order 3 or whatever will give us a point of order 2 or of order 3 in the mod p curve as well, and that will give us a factor of the order mod p. So in other words, the elliptic curve mod p will always contain as a subgroup the image of the torsion subgroup, the set of points of finite order of the curve over the rationals. So that's a sort of an obstruction to primality of the number of points on the elliptic curve mod p. And so there's an interesting question: how often does it occur that that's the only obstacle to primality? In other words, how often does it occur if you fix an elliptic curve E, just your favorite elliptic curve E defined over the rational numbers, like for example, y squared equals x cubed plus x, and vary p and ask for the number of points mod p divided by this small number, which is the number of torsion points on the rational curve. How often is that prime? Is it possible to prove for any fixed E that there are infinitely many p for which this ratio is prime? The answer is nobody has proved that. That's an unsolved problem. There's no example of a curve E for which we can say that that's prime infinitely often. Now this question is sort of, yeah?
Does it say anything about the dual problem? Suppose you fix P and let the curve vary, let's say, ordered by either the J invariant or the discriminant. Is anything known about that problem?
I'll mention that a little bit later. So you mean varying the coefficients?
That's correct.
Yeah. Yeah, again, the answer is no, but I'll get to that. Okay, now this, in addition to having practical interest, because we're looking for curves whose order is divisible by large prime, it's sort of nice, and I think this often happens in this field, that sometimes the same questions that are of practical interest also turn out to have sort of nice historical and theoretical connections. Well, this is closely analogous to a classical unsolved problem of number theory if instead of an elliptic curve, we simply take the non-zero integers multiplicatively, and there the torsion, the finite order integers multiplicatively are plus or minus 1. If we reduce the picture mod p, we're asking about the order of the multiplicative group of integers modulo p divided by the plus or minus 1 group, and that's simply asking about p minus 1 over 2. So I'm trying to show why this is reasonable to consider closely analogous. And we can ask, what's the probability as p varies that p minus 1 over 2 is prime? Such a prime is called a Sophie-Germain prime, that is a prime for which a prime p1 for which twice p1 plus 1 is also prime. And the reason why that was of historical interest is because the first systematic result ever proved on Fermat's last theorem was by Sophie-Germain in the 1820s, and what she proved essentially was the first case of Fermat's last theorem, sort of half of Fermat's last theorem, for primes that have this property, that twice the prime plus 1 is also prime. So for a long time, there was a lot of interest in the question whether Sophie-Germain proved the first case of Fermat's last theorem for an infinite number of primes or not. And this is still an unsolved problem. And so the elliptic curve analog is also completely unapproachable as far as we know. Nobody seems to be close to answering either of those questions. In fact, the original Sophie-Germain problem that's on the middle screen is also of practical interest if you're constructing a Diffie-Hellman key exchange using the multiplicative group of a prime field in the situation that Kevin described. What you might want to look for is, because there also one wants to avoid finite fields whose multiplicative group is not, whose order of multiplicative group, which is p minus 1 in that case, is not divisible by a large prime. You want it to be divisible by as large a prime as possible. And the largest possible prime would be p minus 1 over 2, if that happens to be prime. So this Sophie-Germain question is something you might be interested in sort of the original Diffie-Hellman situation. And just one note, there's a deep result of Barry Mazur from the 70s that says that there are at most 12 torsion points on an elliptic curve over the rational numbers. And this tells us the denominator here is not going to be very much larger than in the Sophie-Germain case. That this denominator will certainly no larger than 12, and most of the time it might be 2 or 3 or 4. So any time this ratio is prime, that means that that prime is very close to the order of the group. Okay, so that's fixing a global field and varying the prime. Another thing you can do, yeah.
This problem is posed here about problems because they have almost no answers. If you take almost any people can construct out of a prime, you can almost never fit that into a prime.
Right.
But in almost every case, there is heuristic argument.
Yeah, here also. The answer is almost certainly yes, and you can make an estimate not only that there are infinitely many, but you can make an estimate of the expectation that it will be prime, and there's some computer evidence and there's some computational evidence for such conjectures. I wrote a paper about that in the late 80s, about the conjecture, about heuristic and computational evidence for the conjecture. No. I don't believe so. But is it 16? Okay. Oh, I see what you're saying. Okay, I'll check that. Thank you. Yeah, no, I should check that. Yeah, and I know where to look it up. So I'll check. Yeah, thanks for bring that to my attention. Okay, so Another approach is to take what I was sort of hinting at before. You just take a small field, elliptic curve over that, very easy to enumerate all the points if you want and count the number of points, and then take field extensions and regard the same elliptic curve as an elliptic curve over a field extension. Now you want to take the field extension, you'd probably want to take the field extension to be of prime order, because if the field extension is of composite order, that is, there's an R prime that divides R, then the elliptic curve considered over that intermediate field will give you a subgroup of the elliptic curve considered over the big field, and that would be a reasonably large obstruction to primality, and so you probably wouldn't want that. So the nicest case is when R is prime, and there the best one can hope for. Again, there's a slight obstruction to primality in that the number of points over the ground field, the small field, that subgroup, that will give you a subgroup that divides a subgroup of the big group, and so there'd be a factor, a small factor that necessarily divides the order of the large group. But it's possible that the ratio could be prime, so that's the best you can hope for. That ratio can be written as the complex square, the square of the complex absolute value of alpha to the r minus 1 over alpha minus 1, where alpha is the root of that characteristic quadratic polynomial that I mentioned before. So again, you have a question, as r varies. So here you have a fixed elliptic curve over a small finite field, and you're varying the extension degree r, and you're letting r vary through prime extension degrees. What is the probability that this number is prime? Can you ever prove there are infinitely many? This, again, is hopeless. That is, nobody can do anything like that. Virtually nothing's known about that question. And this is analogous to the Mersenne prime question. If you, instead of alpha, you look at 2 to the r minus 1, primality of that, trying to prove there are infinitely many Mersenne primes is still an unsolved problem. Again, there are conjectures. I mean, you can make heuristic arguments for this. Okay, and then the third way is the way Bob Silverman was asking about. You fix the field of definition, some large field, and you vary the coefficients. According to Haas's theorem, the number of points falls in a fairly small interval around q plus 1, namely within 2 root q on either side. It's also known that as the elliptic curves range over all elliptic curves, that is, as you vary the coefficients, the number is distributed fairly uniformly, not completely. It sort of drops off a little at the endpoints, but pretty uniformly. And so, roughly speaking, the probability that the number of points on the curve as you vary the random coefficients is prime, or perhaps has a prime factor greater than some lower bound, is essentially the same as the probability that a random integer in an interval of this form is prime. And roughly speaking, the interval we're looking at is an interval of the form q to q plus a constant times root q. So this leads to a problem in analytic number theory, which is, again, an unsolved problem. Namely, can you say anything about the distribution of primes in an interval of the form q plus c root q? It's not even known for any value of c that there always exists a prime in this interval. In other words, analytic number theorists cannot yet prove that that there exists a c such that the interval from q to q plus c root q always contains at least a prime. So
it's known that the failures set q for which there isn't such a c has density 0.
okay, yeah.
Uniform prime number
From the prime number theorem, sure. There are averaging results of that sort, yeah. So if you're going to change q, then you know you're okay on the average. However, if we absolutely fix q once and for all anybody can prove, we might be completely unlucky, and all the numbers in this Hasse interval might be a product of small prime factors, more or less. So although heuristically people are almost certain that that doesn't happen, but we can't prove it. Okay. Okay. But still not for the Hasse interval. Right. Of course, we're talking about proving things in mathematics. You can't say not quite. I mean, everything is not quite. Okay. Okay. Here, let me give an example of a nice choice of elliptic curves that I've been sort of pushing or proposing since 91, and that recently there was some nice work on this done by Jerry Salinas at Crypto 97. This is an example of fixing. This is the second approach to choosing a curve that I mentioned. Fixing a very small field, in this case the field of two elements, in a very particular elliptic curve, and here it is. Alpha is this root of the characteristic polynomial is -1 plus I root 7 over 2. And here, as always in this case where you start over a very small field, it is extremely easy to compute n sub r, that is a number of points on an arbitrary extension. That what it amounts to in practice is generating something which is like a Fibonacci sequence. That is, you just have a recursive formula that will allow you to generate these numbers of points in negligible time. So here are the details in this particular example. And I want to illustrate how, I mean, as far as we know, this is a perfectly usable example for practical cryptography. And yet it's very simple. The equation's extremely simple, and the procedure for counting the number of points is extremely simple. And so n sub r, the number of points on over the field of 2 to the r elements, is given by this formula, 2 to the r plus 1 minus this ar, where the ar is generated by a Fibonacci type formula. And you're looking at prime values of r for which nr equals 4 times a prime number. 4 is n1. That is, the number of points on this curve over the field of two elements is 4. And so you can ask, are there infinitely many prime values of r for which n sub r divided by 4 is prime? And we don't know the answer to that question, but there are certainly some values of r in a range of practical interest for which n sub r over 4 is prime. There are a few possible values that you could use. Okay. Now, since I'm starting to run out of time, I'll skip the section that I said I was going to skip on sort of interesting ties between elliptic curves and other things. And the last thing I want to talk about is why no one knows how to find a factor base, or maybe the second to last thing, because I probably should explain this short. Okay, so the second to last thing I'm going to talk about is why the people seem to think that you could not, there's no way to get started with an index calculus type algorithm for solving the discrete log problem. And in fact, all of the sub-exponential algorithms for the general discrete log problem over in the multiplicative group of a finite field are of index calculus type. I believe that's fair to say. And so it's natural to ask whether this index calculus method could be carried over to elliptic curves. And this is the reason why people have run up against obstacles in doing this. Or this is one reason why. Let's use the example of this particular elliptic curve, y squared plus y equals x cubed minus x, over the field of rational numbers. Now, it so happens, it's a nice group to use, it's a nice example to use because it so happens that the group of rational points is infinite cyclic, generated by the point 0, 0. Using the addition formulas, it's easy to write a simple formula for how to go from n times p to n plus 1 times p, and then tabulate, successively tabulate the points on this elliptic curve over the rational numbers. And so here's the result. What this is the absolute value of the y-coordinate of the point starting with the top one is 7p, the top down to, so these fractions are the y-coordinates, which is absolute value of the y-coordinates. Now, I don't expect you to read these numbers, but all I want you to notice, I mean, they're not very legible from a distance anyway, all I want you to notice is the parabolic appearance. What that means is that the number of digits that you need to write the numerator or the denominator grows quadratically as a function of n. In other words, if you define the height of a point to be the say the maximum of the numerator or denominator of the x or y coordinates, then it turns out that the height of n times p grows super exponentially. That is, like e exponential of a constant times n squared. And it can be shown that this extremely rapid growth of the height of n times p occurs on any elliptic curve for any rational point of infinite order. And the reason why this is sort of discouraging for the index calculus type algorithm is that in order to get started with index calculus, you want to have a reasonably large number of elements in characteristic 0. Like with index calculus, say, in the multiplicative group of the field of p elements, what you do is you look at the elements in that group that are represented by very small numbers in the usual sense. That is, you consider you lift small prime numbers to you lift elements in the finite field to small prime numbers in the usual sense of prime numbers, and then call that your factor base. Or if you're working with polynomials, if you're working over a large field extension of a small field, what you're looking at for your factor base is the set of polynomials of small degree whose coefficients are in the field. So you have to have some way of getting at some subset of your group that is small in some natural sense. And the way this is done normally is to sort of lift the characteristic 0. And the point of this example is that there are going to be very, very few points over the finite field that will lift the characteristic 0 to any reasonably sized elements in characteristic 0. So there's no way that people have been able to see to sort of transfer your algebraic operations from this finite field up to characteristic 0, where you understand what to do better. And this is discussed in some detail in Vic Miller's original Crypto 85 paper. Okay, so the very final thing I want, yeah, question? Yeah, that holds in trace 0, or by that you mean the case where the Nigel Smart and stuff. This will hold, but there's another. See, what happens there is they embed the group into the additive group of the field, and what happens in Menezes, Okamoto, Vanstone is they embed the group into the multiplicative group of some extension field. But that's different from lifting the points to those fields. Okay, so of course this does not say that there's no non-index calculus type of algorithm. Their algorithms are not index calculus type algorithms on the group itself. They're mappings to some other group. Okay. So anyway, the very final thing I wanted to explain was this T-shirt. which has an elliptic curve over the complex numbers, and then the sort of the part of it that's over the real numbers drawn here. And the words, "I love Chaldean poetry." Well, this came about because while we had the workshop for graduate students in June, it came to my attention that, well, there was an awful lot of controversy over whether one could trust elliptic curves as a basis for cryptography, and especially people associated with RSA were raising a lot of questions about that. And in particular, Ron Rivas, who's the R in RSA, publicly stated on the RSA web page that he didn't think it was a good idea to have much confidence in elliptic curves because he said understanding, roughly paraphrasing, understanding elliptic curves is like trying to understand Chaldean poetry. It's a very, very obscure thing. I didn't even know at the time what Chaldean poetry meant, and so I had to ask my wife, who's a historian, and she explained to me that it's actually it's in the Bible. It's a name of a people, Neo-Babylonian ethnic group that ran the region in the 5th or 6th century BC. And anyway, so they wrote these chronicles, and so I looked up see what I could find about the Chaldean Chronicles, and it's actually of the part they've been able to decipher and translate. It's some quite nice stuff. So anyway, so if Rivas insists that Chaldean poetry should be a metaphor for elliptic curves, I decided, well, why not? And so I love Chaldean poetry is a way of expressing enthusiasm for elliptic curves. Okay. Any questions? Yeah.
About 10 years ago, I had an argument with Lynn Edelman about strategies for choosing moduli for RSA or the discrete system, where I was arguing that you should try to choose your function in such a way that you avoid all the bad cases. So you choose e to the 2 - 1 as a Lorentz constant. And he said, no, you shouldn't do that, because by doing so, you automatically steer yourself into a special case. And the strength of RSA is based on the fact that generic products of 2 times are hard to calculate. So you should just stick completely random numbers with your products of 2 times. So I have a question for you. In choosing elliptic curves, this method that Jerry proposed for choosing specific curve, a very specific curve, you specialize yourself in a very narrow subset instead of all of the curves you can use. So if you were to take one Edelman's approach, you would just use a random elliptic curve. Just hope that it works. What do you think is more appropriate?
Well, there's sort of a philosophical difference of opinion along those lines. Some people say that you want to have maximum amount of randomness. What happens, the advantage of choosing this particular family of elliptic curves, these anomalous binary curves, as they're sometimes called, is that there's certain efficiency advantages. So you could argue in general, just philosophically, that there's more chance, just speculatively, in the year 2020 or something, that somebody will come up for an algorithm for a particular class of elliptic curves than for a randomly generated elliptic curve. Nobody has any idea, as far as I know, about how to do that, but one could argue that there's more likelihood of that. And so just to avoid that possibility, make the coefficients random. On the other hand, if you're producing something for someone who wants to use it, who's not all that worried about what happens in the year 2020 and cares a lot about efficiency today, then you might as well not worry about these sort of speculative possibilities and use this particular family of elliptic curves that has some efficiency advantages. So at least my view is that it's a good idea to do both and to allow the user the option of using something that is a little bit faster, but conceivably at some future time might lose its security, versus something that is a little bit slower, but some people might feel that they have more confidence in.
It's already lost its security.
Whose? Which?
A particular curve. Doesn't matter what the curve is. Because once you've broken a discrete log problem for that particular curve, breaking additional discrete log problems on that curve becomes increasingly when you use Pollard Road, you build up this very large database of distinguished points. Having built this database initially for one discrete log problem on a particular curve, if you now try to solve additional discrete log problems on that elliptic curve, you continue building on that already existing database. It turns out that breaking additional problems becomes progressively easier.
But to make your original database, you can't do it in sub-exponential time, right?
You can't, but what I'm saying is you have many, many people sharing curves. Okay, it becomes more productive to throw resources at breaking one particular curve. And then breaking it for additional people all sharing those curves becomes progressively easier.
Well, I guess I don't agree with that logic, because I think that if you're dealing in a situation where you it requires you purely exponential time, then at the very worst, if you just put in a few more digits in your key size, you will put the problem so far out of the range where even if you have millions of users using all their computers, you're still not going to be able to build up your initial database. So it seems to me that at most, what the argument you're making, in other words, the scenario you're depicting, would be an argument for maybe instead of using 50-digit key sizes, using 60 or 70-digit key sizes. I don't see it as an argument for entirely avoiding the use of one particular elliptic curve. So you're saying that if there exists a database, even if it takes exponential time to come up with it, such that if you have that database, then you can do a lot of things with it. That's not good. I mean, you're proposing sort of a strong, or you're referring to a rather strong criteria that not so much from a practical standpoint, but that it would be nice to have a situation where there doesn't exist any database, no matter how much time it would take to come up with it, that would make the problem easier, something like that.
Mike William knows a little more about this than I do, but for any particular elliptic curve, to solve k instances in a discrete log problem, it takes square root of k times as much work as to solve one instance using Pollard Road.
Okay, but if to solve one instance takes more than the lifetime of the universe, how will that help you?
It doesn't, assuming your key size is sufficiently large.
Right.
But current key sizes aren't really that large. Because 160 bits really isn't large enough.
Okay, well that's a good point. I can see the logic of saying that you should increase the key size just to be safer against all sorts of things, massively parallel attacks and building up of a database when there's multiple use and so on. Yeah, that makes sense to me. But I just didn't see it as